All right, we're back. This is AP Physics 1, check-in number 8 on rotational energy and momentum. So let's take a look at some of the questions that were assigned. Here we have a situation where you want to compare two things. A box sliding down a frictionless surface, so it slides without friction, and then the other one has a rolling ball, rolls down without slipping down the surface. And it says compare the speeds, the linear speeds of both objects at the bottom. Well, to do that, basically we're utilizing the idea of energy conservation, E equals E prime. We know that for the sliding without slip or without friction down there, we're going to say that it's the change in potential energy that's going to turn into the kinetic, so that it's going to drop and it's going to have an mg times h, change in height if you want to go that direction, equals 1/2 mv prime squared. And so your velocity at the bottom is just equal to 2gh square root. Okay. Now, in the case of slide or rolling down the hill, it will have some of this kinetic energy. Wouldn't you agree that it would have not all that, because some of the kinetic energy has turned into, in the second case, if you say E equals E prime, it's going to have the potential energy, but now it's got that translational 1/2 mv squared, but it also has rotational 1/2 I omega squared. So the V at the bottom is actually going to be less for this case. So we're going to say the V of sliding is greater than the V for the rolling case. So that's just a straight comparison of just looking at the two, because the one is just translating and the other has to translate and rotate at the same. So we're going to say the speed for the sliding case is actually greater than that. It's just something for you to think about. Another classic angular momentum type situation is the situation where you have a set of disks. One is originally above, the other is not moving. The second one's on the bottom, it's rotating at 5 meters per second. They have different moments of inertia. So this has a rotational or moment of inertia of 3 I naught. The one on the bottom is I naught. And eventually they're going to, this is going to fall down on the other and they're going to rotate together. To me, it sounds a lot like an inelastic collision where the two collide and move together as a group. And you want to know, what is their combined angular speed? Well, the idea is that we're going to use angular momentum conservation, L equals L prime. So in this case, it's going to be the I times omega of the first plus the I times omega of the second. And then afterwards you have I times omega prime plus the I2 times the new omega prime. Remember that when we did inelastic collisions, those two, since they're moving together, will have the same velocity. Okay. The deal is that the second one is 0 before, so this is going to be I naught times 5 radians per second. And then we're going to have a 0 here. And afterwards, this is going to be, wouldn't it be true that you would just factor that out? So it's going to be 3 I naught plus I naught times that factored out angular velocity, because they both have the same. See if mathematically that makes sense to you. But over here, this is going to be 5 I naught equals 3 plus 1 is 4 I naught times omega prime. The I naught, it doesn't even matter what that number was. At the end of the day, the final angular speed is just going to be 5 over 4, which is 1.25. And that's going to be in radians per second. So that should be the answer to that question. Does that make sense that that would be true? Well, they have an initial angular speed of 5. Afterwards, together, they should be quite a bit less. And in fact, that is true. Okay. So that's that question. The last question we have on this one is a little bit more challenging, but it's something that's come up before in the AP Physics 1 test recently, is that if you take an object and you shoot it into like a meter stick, piece of clay hits the meter stick and then it raises up. And the idea is going to rotate about the point at the top. So you can use angular momentum conservation to figure out this problem. And so it says here all the data. You have the mass of the piece of clay, its initial velocity, the mass of the meter stick, its initial velocity, which is 0 because it's not moving, and then the length of the meter. In this case, it's probably not a meter stick because it's over that, but the length of the stick itself is 1.25 meters. Okay. So it says, what is the initial angular momentum of the clay? And this is something that's pretty difficult for students to realize, is that it's not rotating, but relative to that point over here, it has angular momentum in the system. And that angular momentum is going to be equal to the mass of the clay times the velocity of the clay times the radius, which would be, when it hits it, how far is it from the point of leverage, lever arm, if you will, from that would cause it to rotate. So in this case, if we put some numbers down, let's see what we get. This is that's 0.25 kilograms. It's got an initial velocity of 7.5 meters per second. And it's got that 1.25 meters of a lever arm. And if you do that, you get 2.344, and then the units would be kilogram meter squared per second. Okay. The next question is, what is the final angular momentum of the system? Well, I'm just going to write in here that the final angular momentum has to be equal to the initial angular momentum. So the answer to that would also have to be 2.344 kilogram meter squared per second. So that was really just a statement of fact rather than a calculation. Okay. The last one is, what would be the final velocity of the two of them together as they take off and they rotate? Okay, so think about that for a second. And the idea here is that if you say L initial equals L final, we've already figured out what the numbers are, but the final angular momentum would be equal to the angular momentum of the piece of clay plus the angular momentum of the stick afterwards. And so you have to just keep that together. This is going to be I of the clay. That should not be class. I don't know why I wrote the word class, but clay times the angular velocity plus the stick times the angular velocity. This is again your mvr, and that's omega prime, and then this would be I times omega. So you'd have to do a little bit of work to do it. I haven't told you a lot about how that's going to happen in class, but the meter stick itself is going to have a stick is across, from the point here, a piece of stick is going to have a moment of inertia of 1/3 ml squared. And then you can go ahead and put these two together. I think that should just be like m times v times r. Excuse me for writing that omega prime, but that v is equal to r times omega. So you can actually put that together, and it ends up being m r squared omega prime for that. And then you're going to use the 1/3 ml squared. You can actually calculate that from the numbers that I gave you. So the final angular momentum turns out to be, and you'd have to calculate it, 0.25 kilograms. R squared is 1.25 meters, quantity squared. And then you have this omega prime plus the 1/3 mass of the meter stick is 0.75 kilograms. Omega L is 1.25 meters. And then that's also times omega square prime. That's squared. Okay? So you calculate that out. So you have your number on this side, which is 2.344. And then you have to do a bunch of math with these. You'd have to do your calculations. And just to make a long story short, I end up with 3.16 radians per second. I ask you to go back through and make sure that that makes sense. But if we had more time, I would talk you through how we got 1/3 ml squared. But I think that's something that you should be able to take your numbers and make sense of. Okay? Hope that worked out for you. We'll talk to you the next time. Thanks. Stay safe.